So hello everyone. Okay, we're recording. So what we'll do today is we'll continue from the f-GANs. We have derived the objective from the for f-divergence, the Fenkel's divergence, and we've shown the what is a Fenkel's conjugate and things like that. And today what we'll do is we will derive the FJ's divergence based f-GAN, and we'll show that it is equal to the DC-GAN. And as homework, I'll give you a few more matrix like the Kale divergence as the reverse Kale and the chi-square GANs, which you can derive and do in the same procedure. They're the much simpler, and then they are much simpler to compute, and you can do them as exercise, which may be one of your assignment problems. So what I'll do today is let us get started from where we left off. In the end of last class, I told you that I will show you this. We came up with solving the Euler-Lagrange equation. So we showed that D go into so what we'll have the agenda for today is to do the f-GAN and then see variants of GANs and complete most of GANs today, and then so that in the next session we'll be starting off with autoregressive models after doing Wasserstein GANs. So yeah, so that's the agenda. I'm not doing a recap today because it's a continuation of the previous sessions, and only once you'll be able to end this session will you have the entire picture of GANs. So we know that this is if T contains all possible functions. So then it is defined as a supremum over if one function of T from the entire set of functions. And we have the expected value of Tx minus the expected value of the sampled from the other distribution f star of or the conjugate of Tx. And we showed that using the Euler-Lagrange equation, that is dl dt minus dt dash ddx of dt dash of L is equal to 0, that the optimal function, that the T opt that I have for a particular f divergence to convert. So what does T do? So if you're again trying to recall, remember that our function, so we derived this by, if you recall, we said that df of P and Q, just a quick recap, is Q of x, f of Px by Qx dx. And we said that instead of having f, we will have the conjugate of f. So we will have integral of Q of x, f double star of x, the Fenkel's conjugate. And we said that this is nothing but equal to supremum of T belonging to domain of f star. It's just writing the conjugate function P of Px by Qx minus f star of T. So this is what we derived, and this is once we take the supremum out over all functions, we get this equation, right? So we said that, okay, so that this T we know is a function of x. So we could define a function T which takes in values of x and gives me in the domain of x, which takes a function in the domain of fx. So here it's domain of f star, or rather we can say that it takes a value in x and converts it into the domain of t star, f star, right? If this is t, and this is the domain of the t is a function that takes the value in the domain of x, right? So all the values that the x was taking, it will take that value for corresponding values of x. So whatever value we had here for x, there will be a particular value of t that maximizes this equation. So it will convert it to the domain of f star. And then, so we presented this t. We said that t is nothing but t of x. So which will be as a function of x, and it will become more clear because it's a supremum function as we derive that the derivative of the conjugate is equal to the derivative of the inverse function. So we'll see that, or the inverse of the derivative function. So let's see that and try to appreciate what this derivative means. So first thing that I'm trying to show is when we solve this equation. So when we solve this equation that I have into qx. So if you have qx here, if you take qx inside, so you will have this equation as supremum of t belonging to t, or t as a function of x belonging to this set of functions. And this is lower bounded because we may not have access to all functions as we discussed last time. So p of x minus f star of t of x, q of x. Right, and then we just take a derivative with respect to this, and we say that dl dt minus ddx of dl dt dash is equal to 0. This is equal to 0 because it does not depend on the derivative. L does not depend on derivatives, so this becomes, we have derived this f star dash of t optimal of x is equal to p by q. So now let's try to find out, and my claim is the lemma is this, the optimal function that I have, that the t optimal that gives me the conjugate values for every that will give me the conjugate value is given by f the derivatives inverse, or rather, sorry, just the derivative of this. So what my claim is, so if I take the inverse of this function, f star dash inverse is nothing but the derivative of the function. This is my lemma claim. So let's try and prove this. So before I prove that, let's complete the formulation. It's a saddle point operation. So we know that, so say this t in neural networks, right? So because we've already done this before multiple times, we can just complete it in a go. So my df of p and q is a function of, say, theta, right? Because this is a generator function, generator distribution, right? This is going to be given by, supremum over w. Say I'll parameterize t with a w network. Right. So this is going to give me that will take a value of x in the input, the domain of x, and t of w would give me a value in the domain of f star. So this is what it will give me, and it is going to give me supremum of the expected value of tw of x belongs to p, minus the expected value of q, where x belongs to q star or q theta tw of x. Right, I'm just parameterizing this, and now what I'm saying that this is hoping all functions exist. So I'll define in this form. So this is, it can be a lower bound, but I'm being hopeful and putting the equality really doesn't matter. We can only optimize for the right hand side. So now I'm saying that, okay, that I have access to, I have this supremum function that I've already have, but I also want to minimize the df, the divergence between p and q theta, right? So now, therefore, the theta star that I have over and the w star that I have over will be infimum over theta, or the minimum over theta. And we have the DKL divergence, supremum over w, and we have this entire equation, which I'll just copy. time consuming to write it and to retype. Copied, and this is when I'll paste it. Yeah. Right. So what you can see here clearly is, so this is my KDF. So I'm minimizing over DF, but it turns out to be a min-max game. And that we have seen by intuition as well. And therefore we have this discriminator and generator thing that will also come up. So let's stop there and let's solve this lemma, because we have shown that this is true, but the book claims, or the paper claims, that the T optimal is just given by the derivative of the f function. So our assumptions are, as we have already always taken the assumptions, let's put a thing over here, assumptions for proving lemma for lemma 1. So let me just write this down, sorry. So this is, say, lemma 1. It's very interesting. So this is just a cognitive task here to do this. There's a mathematical task. So we haven't done calculus for a while, and it's like going to be revision of calculus 101 of univariate calculus of your school days. So let's just do this proof, and just for lightening up the mood before we go into complicated derivations of GANs. So we know that the f star of x, right? The f star of x is equal to, right? We know that the f star of x, just a moment for me. Just a moment, where did I write it down? F star. Yeah. This is, I think this is correct. Is this correct? F star inverse. Yeah, that is correct. So let's do that. So f star of x is defined by supremum of over y. So, okay. Y belongs to domain of f xy minus fy. Right? Very nice. So now, as soon as I have this, but if I have to find a supremum, we assume this is my conjugate, f conjugate. Assume f star exists, f dash exists, f function f is differentiable and convex. And we have shown that if it is differentiable and convex, that is continuous and convex, f double star of x is equal to f. So we have shown that the conjugate of the conjugate is the function itself, but this is more that we are trying to prove. So, okay, let's try to find out the supremum. So this is, let this be the objective of y. So so let's just do dl dy and set it to 0. And what we will see is, so therefore it is x minus f dash of y is equal to 0, which gives me x is equal to f dash of y. So as soon as I get this, so this is one equation that I get, and therefore I can write, so on my right, I can write f star of x in terms of y, so that we don't mix things up. F star of x is equal to, so I'll just put the value of x here. So I can do f dash inverse and put the value, which I'll not do because I won't want to put in a lot of notations. So what will I do? I will write this as f dash of y into y. I'm just putting the value of x here, just substitute x is equal to f dash y into y minus f of y. So that you can see this is all a function of y now on this right hand side, all function of y. But what we need really is the derivative with respect to x. We need this. All we need is ddx of f dash of x, right? So this is ddx of f dash of y, right? and the whole derivative with this minus f of y. So now you'll tell me, okay, isn't it 0? I'll say no, because x and y are related by this operation. So x and y are related because we have this. So let's see what is ddx of f dash x. So if I take the derivative of ddx, this is equal to f dash or f double dash y by chain rule into dy dx, right? So which I can write as dx. So this is equal to 1. So I can write dx dy is equal to f double dash y. Okay, so this I can write. So now let us try and take the derivative on this side. So this is a relation that I have from this. And let's take this derivative using chain rule. And what do I see? I see f double dash y, right? First the UV rule into dy dx, right? This is the derivative of this function into y plus f dash y into, this is so interesting. This is just basic 101 calculus, but it's so nice to do this. So we'll have df dx or f dash y dy dx, right? So this is what I have. As soon as I have this, what can I write? So now I can write a few things. So this is dy dx, right? So dy dx is, we can write dy dx as 1 by f double dash y, isn't it? So clearly from this equation, I can write this inverse. And once I write that, I can put this value as y into f double dash y by f double dash y. I'm just putting this value over here, plus f dash y into dy dx. So we know what is f dash y into dy dx. We know dy dx is, am I doing this correctly? So the derivative of y with respect to x, yeah, I think this is fine. So I can write this as, let's keep this dy dx for the time being, minus f dash y into dy dx, right? Is this correct? Did we write this correctly? This term, take, yeah. So this becomes equal to, so I can cancel these two, and this is y, right? So this is y. And what is this? This term as well goes to 0. This and this will cancel, and this will go to 0, so that you have, this is equal to y, which means ddx of f dash, or we can just write f dash x is equal to y. And what is y? If you recall, this y, this value of y is nothing but f dash. So from this equation that I have over here, the value of y is f dash inverse of x, right? So this is very, very simply done. So this is what I wanted to prove. So now you can see, so I have this equation. So from this is from star. So I have f star dash of x is equal to f dash inverse of x, right? So now, which means this is an inverse function, right? So the inverse, so comparing functions on both sides, functions we get, the derivative of the conjugate is equal to the inverse of the derivative. This and this, because both are the same parameters x. So this is what I wanted to prove. So if I take inverse again, this was the original equation, original plan that I have. So the original equation that I wanted to have is, if I have the inverse of this again, okay, let us keep this and this. So this is equal to f dash if I put an inverse on both sides. Star dash inverse, right? I put an inverse on both sides, inverting, assuming inverses exists, because it's a convex 1-1 function, assuming inverses exist. So this is all, and hence QED. Right? We have proved this, what we wanted to prove. Right? Very nice. So now once we are able to prove this, so I can use this value that I have over here. So in the original equation, we found out f star dash of p by x, or t optimal, t opt of x. Where is it? Here it is equal to p by q, px by qx, right? So now if I want to take an inverse of this, f star dash inverse of f star dash of t of opt of x, this is equal to t opt of x. This is clearly I'm taking t star dash inverse px by qx, which is equal to, and I have shown that this is equal to the f dash of px by qx. Hence proved. So my optimal, the t function that I want to learn is the derivative of the conjugate function and the ratio of the ratio. So it's a very, very interesting result that the discriminator t function, tw function at optimality learns the pointwise values of the derivative of the ratio, pointwise function value, sorry, pointwise derivative of the function value at p by q x ratio. Okay, this is what we end up learning. That we find out the ratio, take the derivative and compute the value at p by q at that point, and that's the ratio that t opt tries to find out. The ratio of the two distributions that I have at hand, and the derivative of the Fenkel's function. The function is the f function. So let's now do this optimization. So we have shown this, we have shown this, we have shown the saddle point equation, and we have shown the GAN objective. Now let us try to find out, now using f of u equal to the J's divergence matrix. Now using it to get the J's divergence matrix, we have to derive the standard GAN. And your homework is for chi-square and KL divergence. So let's derive. So let f of u is equal to u plus 1 log u plus 1 by 2 plus u log u. And we have to find out, using this, derive the standard GAN objective. And why, you may ask me, why is this important? Is because this is telling you that you're defining a metric on which you are doing your GAN. It's not a discriminator actor and a generator game. It can change according to your value. It can, your GAN can be updated based on choice of f and hence T optimal also changes. So this is, but the J's divergence is more difficult to compute, so therefore we'll do that. So let's try to find out. So we remember df of P and Q is given by the supremum of T belongs to T. This T is a set of functions, and this is a particular function dx. Sorry, where's this thing? Yeah, the expected value of x from P, T of x minus the expected value of x from Q, f star of dx. So let's try and find out. So what we need is value of f star. That's all we need. We need f star conjugates to find the loss function. Okay. So let's try and do that. So f star of, say, u is the, say, let's take, what variable should I take? Should I take t or u? Okay, let me take t. It's easy to remove. So f star of t is domain of supremum of u belongs to domain of f, right? ut minus fu, right? It's, as you have multiple times seen, that it's the maximum of the difference between the line at slope u minus the function values at that value u, and you compute it across all the values, and then you at slope t, sorry, in this case at slope t, and you see the line and the function value, where is the maximum difference between the, so you have a function like this, you have a function like this, and you have a line defined by parameter t. So you see wherever the function f and that line has maximum distance, that is the value of the conjugate function. We've seen it last time. So, okay, so let's find out the supremum. Let's put the values that we know. So this is ut. So my L of u is defined as ut minus of u plus 1 log of u plus 1 by 2 plus u log u. Okay, so now dl dt, oh sorry, dl du is equal to t minus what is this value? Remember, we are trying to find the optimal u in terms of t, right? So let's try and do that. T minus, so if I take that using the chain rule or UV rule first and the chain rule then, I can write this as plus 1 minus 1 plus log u, right? So all I did was take the derivative of the log. This is also minus. So this, we know that x log x, if you take derivative with respect to x, or u log u with respect to u, is equal to log u plus u by u, which is equal to 1 plus log u. So that's what I've been using here, 1 plus log u. And since we have the internal function is also a function of half and all, so that also gets cancelled out. It's not, it doesn't really change anything, because there's 1 by u and then that cancels it out in the outer summation. There's 2's everywhere. Yeah. So now this is equal to 0, which means this 1 and 1 gets cancelled. So t is no equal to, is it correct? So no, this is plus. This is a minus and minus gets positive. And so this is plus, and then you get t is equal to log of u by u plus 1, 2. Is this right? I think so. Yeah, if this is this and that is, yeah. So I get e to the power t is equal to u by 2u by u plus 1, or I get u by u plus 1 is equal to e to the power t by 2, e to the power t by 2, which also means by dividendo u is equal to e to the power t by 2 minus e to the power t. Very nice. So I got this equation all right. And now I can easily, if I can find u, I can find out f star of t. F star of t is therefore I've got the supremum value. I'll just put this is my t u opt. So my u opt, I'll just put the value of u opt and I'll get t times e to the power t by 2 minus e to the power t plus e to the power t by 2 minus e to the power t plus 1, right? This is my u minus 1, u plus 1's value, log of e to the power t by 2 minus e to the power t plus 1 by 2. Just putting the values of u. This is u plus 1. This is u plus 1 by 2 minus e to the power t by 2 minus e to the power t log of e to the power t by 2 minus e to the power t u log u. Okay, so now I can clearly simplify this better. T to the power t to the power t 2 minus e to the power t. Okay, and as soon as I do that, you can see a clear thing that comes up over here. So I will get, if I separate out the numerator and the denominator over here, so I can see that I can write e to the power t by 2 minus e to the power t. This comes from the numerator here, the numerator over here. So if I numerator this term over here can be written as e to the power t by 2 minus e to the power t log of e to the power t minus 1 by 2 minus e to the power t log of 2 minus e to the power t, right? So I just wrote it in terms of two terms, and this is plus, sorry, you're multiplying, right? So yeah, so this is how we can write this. So these two terms go away, and my second term stays. So second term is 2 by e to the power 2 minus e to the power t log of, I will have the same thing inside the log because it's the same function divided by 2. So I'll have 1 by 2 to the power minus t, to the power t, e to the power t. And I will have negative of 1 by 2 to the power e to the power minus t. Okay. Into log of 1 by 2 to 2 minus e to the power t, right? This is what I'll have. So what does this turn out to be? So I'm using this term, right? I'm using this term and I'm using this term over here. So if I use these two terms, what will I get? I'll get 1 by 2 minus e to the power t log of, so am I doing the correct calculations correctly? I think there's an e to the power t somewhere. Yes, I missed it. Sorry. So there's this e to the power t over here, right? So the e to the power t is also there in this second part. I missed that out. E to the power t, sorry. So e to the power t, and if I miss that out, then I'm a little bit of a problem, e to the power t, right? So now I will have 2 minus e to the power t. So this term and this term Both are the same with the different coefficients of log of 2 minus e to the power t, which gives me minus log of 2 minus e to the power t. This is my f star of t. Wow. So now I have an answer to my question. So my answer is f star of t is this. So therefore my equation of df, p and q would become supremum over tw or over w. I'm going to parameterize using w. Okay, so now let's do this. So it is expected value of x from px, tw of x minus the expected value of along to q. You can write put q theta now, q theta log of, and you have a minus over here. So minus and minus gets plus log of 2 minus e to the power t w of x. So now there is a problem of selecting this as the tw function. So now if there's a problem, this neural networks tw can only take values in rd and output r. So therefore 2 minus e to the power tw x is not defined, is only defined for if it is greater than 0, right? It's a log function. The domain of this is defined for. So you have to be very, very careful. What do you have to be careful for? See, this tw function that I have, tw function has to be a composition of an activation function and a neural network, right? You can put f or anything, but it is an activation function where g will take values because fw is a neural network which takes in x and returns real number. So this will take a real number and give an output in the domain of f star. Because you can clearly see that the f star function that I have is a function of this tw function. And if you have tw in f star, this domain would, if you have real value, like if x is tw is equal to just 3 over here, for example, e to the power tw is 3, then what would end up happening is 2 minus 3 is minus 1. Log of minus 1 is not defined. So this function would not be defined. To make the function be defined, we have to put an activation function over the end of the neural network so that it projects it onto the domain of f star. So now let's see what is the domain of f star. Domain of f star for JS, Jensen-Shannon divergence. So for if you want to find the domain of f star, we know log is a function that takes in value from r plus and outputs r. So my domain is r plus. So 2 minus, because we know that a function is like this, right? It's not defined for negative values of. So t minus 2 minus e to the power tw of x is going to be, has to be greater than 0, right? In other words, tw of x, if I take log on both sides, has to be less than equal to log 2, right? So has to be less than log 2. Right, it can be anything. So tw can be any value from minus infinity to log 2, right? So now how can I do that? So if I have to have a value between minus infinity and log 2, I can do that using a combination of something. So what can it be? So again, tw of x, can I write this, if you can tell me, as this function? So this has to be less than log 2, right? So now, can I write it like this? As tw of x, right, is log 2 plus something that is less than 0. Right? Can I write this way? So I have to put TW of x to be less than log 2. So therefore I put the cap of log 2 on the value on the function, and I'm putting a value that is less than 0 on the function itself. So can I put log of the sigmoid function of some neural network? So this sigmoid of fw of x is defined by 1 plus e to the power minus fwx, which takes in sigmoid, takes in value from R and outputs between 0 and 1. We know that it's outputs a probability, right? So this is my sigmoid function. So as soon as I do that, if my log is between 0 and 1, then this function log of x is less than 0 for x between 0 and 1, right? And I have put the sigmoid activation function on the neural network and put it over log to get the value less than 0. So now it's very clear. So what is my TW function? My TW function is log of 2 by 1 plus e to the power minus fwx. If I do this, it's clearly less than equal to log 2. So this TW of x gives me less than equal to log 2. Very good. So now I have the activation function TW of x I know. Let us now try to find out, and I know it in terms of this neural network outputs a real number. Okay. So always remember, after you get the conjugate function, you have to have an activation function so that your neural network outputs in the domain of the conjugate function, right? So let's now put the values back into the equation. So again, I will write down the, let's just copy okay. So this is my, sorry. Okay. So I know this function. I'll put the value of TWX. Let's just put the value at one go. If I put the value of this, what does it become? Supremum over W, the expected value of X from P. Or we'll just put PX directly now. PX log of 2 by, also I can, instead of putting all this complicated things, I can just say log of 1 by 1 plus e to the power minus dwf. Just a moment. Sorry, there was a emergency call. Okay, so this becomes this, and I have some constant log 2s to take out. I just pulled this log 2 out because it's a constant. So now plus the expected value of x belongs to q theta log of 2 minus, now e to the power log, so t, this is log of something. So this value you can just put directly over here. So e to the power exponent of log of x is equal to just x. So therefore, I can just put 2 by 1 plus e to the power minus fwx. Right? Again, I will take this 2 common. I'll pull this out and I will have 2 log 2 plus the expected value of supremum constants can be just pulled out. The expected value of x, px, log of sigmoid of fw of x plus the expected value of x belongs to, sorry, x belongs to q of theta log of 1 minus sigma of fw of x. Clearly, this is my discriminator, d of x. So d of x is a discriminator which predicting +1 for px, 0 for p theta or q theta. So this is equal to dx and this is equal to dx. So if this is dx, and so my equation is, so therefore the objective becomes the DC-GAN or Goodfellow GAN djs of p and px and q theta, the minimum over theta, right, is equal to, this is just minimization of the f divergence, minimization of j's divergence. This is equal to minimum of over theta, maximum over w. Let's put the w on d. Expected value of x from px log dw of x plus the expected value of q theta 1 minus log of 1 minus dw of x. Okay, so that's all we have seen, and this is the GAN objective. So with that, we have understood what f-GANs are, and the rest of the 1 hour, what we'll do now is try to understand variants of GAN and its implementations, interpretations. This will be very quick, and then we'll learn a few concepts here and there. So recall the objective of the classical GAN, therefore, is this. Or do I have the diagram? No, it's better since I have already derived this. I'll just draw the diagram over here once again. So there's this generator function which takes in a value of z from a stereotypical distribution and outputs x fake belonging to q theta, whatever you have, p theta, q theta, right? And then you have this x being sampled from px, and you pass these two together to a discriminator d, which gives real or fake images. And the discriminator tries to predict between real and fake images, where the generator tries to maximize the loss. This is, you can clearly see the opposite objectives, as we just now proved. Okay, and we have also known that is equivalent to minimizing the JS divergence and so on. And now we have also shown that the discriminator star is px by qx, right? So we have shown that the discriminator of x is nothing but the probability of y being in the positive class for a fixed generator. We have shown this again last time. This is just to recall the base classifier. This is nothing but equal to p of x given y equal to 1 into p of y equal to 1 by the ditto this thing plus p of x y equal to 0, p of y equal to 0. So we know that given y equal to 1, this is nothing but the distribution of x, the real data. This is nothing but the distribution of q theta, and these are all equal to half because it can either be in the real data or the fake data, and the amounts of real data and fake data are equal. So this turns out to be px of x by px of x plus q theta of x. So this we have already shown for an optimal discriminator. For an optimal discriminator, this is always going to be in this form, right? This is what we have already shown. So okay. And now at optimality, px equal to q theta, and we have this as d star of x as px by px plus qpx. This is equal to half. So always going to predict with a probability half. That is always, it has no chance of predicting whether it is in this true or the true distribution or the real distribution. So it's always going to give me a half output. So it's always 50-50. Half of the times it will say one class, half of the class times it will say another class, but it's always going to be independently wrong about both of them. So okay, that's a trick to when you're training GANs, you should see the discriminator should have a loss of half. And we have shown that it should not become too powerful. If it does, then it has vanishing gradient problems, and you have to use the DC-GAN objective where we just do away with this one minus and put a minus at the end and so on. But okay. And the minimum, it could also, a minimum of the J's divergence, this could be 0 or log 2 or 2 log 2, depending on your equation. So if you have this equation, if you optimize for this, you consider this as your objective, because we have already see, remember that we have dropped that log 2's in the equation. No, we had a 2 log 2 term. So now if I put this is equal to 0.5 and this is equal to 0.5, what do I get? I get log 2, 2 log 2, right? 0.5 is just half. So half and half. So log half is minus log 2, and minus 2 times is 2 log 2, right? So this is 2 log 2 if it's one of the cases, or 0 if you just keep the other way. So if you keep minus 2 log 2 in the previous equation, you remember in our previous function, we had this constant over here. If you keep minus 2 log 2, if you're maximizing, so if you minimize your minus 2 log 2, so then it's 0. And that can be seen if you just put the value of the J's divergence. So depending on what your objective function is, if you have a constant added, if you don't have the constant added, you will see that your 2 log 2 is the loss that you're getting in your computation. When you are, it's around 1.4, 1.5 is the loss that we'll always have at optimality for the discriminator. Okay, because 0.68 is, I think, log 2, if I'm not mistaken. So it'll be around 1.4, and you'll be like, yeah, this is theoretical boundary that I have of the loss. So now if you remove the offset, then it's equal to the J's divergence, and then this becomes px, because this px by qx by 2 is 2px by 2, and this is dkl plus dkl q theta. So this is 0. So if you remove the offset, it can either be 0, if you, depending on whether you present or offset is present or not. Mostly offset is not present, so people in the literature say that it's offset at optimality is 2 log 2. Okay, so now there's an alternative view to optimizing GANs. The alternative view is using these this Bayes classifier idea. The idea that the Bayes classifier exists, and you are training a model h theta, which takes in again a real value x, a real data, and says it's a real or a fake data. If you have such a classifier, then that's all it takes. And what you're actually optimizing for, and you have, say you have access to ratio of the, if you have access to the ratio of the densities, then that is px by q theta of x, the real versus generated densities. So what it is actually, it is actually optimizing a function over the risk minimization over this H function, which is a discriminator. Let's try to understand that. So we know for a fixed generator theta, let's put q theta over here, which learns the distribution q theta. My optimal discriminator, or h star of x, which I'll represent by h theta, or d star of x, which I'll represent by h theta of x, which I'm actually learning, is given by, which is just now we showed that, is equal to px of x, or just px in this question, by px plus qx. Right? This is what is known to me. And as soon as it's known to me, see, also what is known to me is the ratio of the densities. And I have only access to the ratio of the densities as px by q theta of x. If I have access to the ratio of the densities somehow, so then what do I do? And if I don't have access to this discriminator and so on, so then what do I do? Then it's very simple, right? So using the ratio of densities as well, the point claim is using ratio of densities as well, comma, we can train a GAN. Can train a generative adversarial neural network. Okay, so let's try and write down h theta of x is equal to px by px plus q theta of x. What I'll do is I'll divide by q theta, so I'll get px by q theta of x by 1 plus px by q theta of x, assuming q theta of x is not equal to 0 and total support of q theta. This is no loss of support for the x variable. So in this case, this is nothing but the r theta of x. This is 1 plus r theta of x. Right? So now this is my h theta of x. So now what I'm trying to do is that I'm going to minimize. So this is my, whatever the objective that I had, the h theta of x, is this likelihood that I had over here, right? This likelihood densities, if I'm going to do maximum likelihood estimation, this is a maximize the likelihood, the likelihood of h theta of x. Therefore, theta star, or I can just put h theta star, is the arg max of h, right? Or you can just say arg max of a theta, r theta x by 1 plus r theta of x. So, right, so we have access to r theta when this is nothing but h theta of x is what I'm trying to maximize. So which is equivalent to saying arg min over theta minus of r theta of x by 1 plus r theta of x. So now this is for the discriminator. For the generator, what I'll do is I'll try to maximize this equation since it is the opposite. Generator tries to do the opposite. So you'll get q star and h theta star. So this is an alternative view to seeing GANs in terms of the ratio function between the densities. So once you have seen these densities, the discriminator is, so this is the takeaway from here is in normal circumstances, you often end up training h theta. And there, if you want to find out the densities of px by qx, right, which is nothing but r theta of x, this is equivalent to taking dividendo in this equation, dividendo, and saying h theta of x by 1 minus h theta of x. So you can do either you train a discriminator, and the discriminator, you can find out the ratio of the densities from the discriminator, or what you can do is you can train a generator, or you can train a model that predicts the ratio somehow, and then that's generally not done. You use a discriminator anyways, but if somebody in Oracle gives you the ratios, you will take r by r plus 1 plus r, minimize that objective, right? So this is an alternative view to seeing GANs. So these are all like theoretical views of the GANs. Now let us try and see some practical implementations of the GAN. Some GAN models which have been very, very popular in the literature and has been what do you say? These models have been have been seminal papers, and they have been used to understand data better. So we remember we have done Info-VAE, right? It's like an Info-VAE. We are going to do like an Info-GAN here as well. So in Info-VAE, we said in Info-VAE, we wanted latents to have maximum information about data, so that it could be used for compression, hence downstream tasks like prediction. So let's see. So if it could be used for compression, and then use those latents for predicting, as we have seen in the you could have different clusters and use this training data to actually predict on that. So that's fine. So the Info-GAN is what the Info-GAN is going to do is, remember, this GAN at the end of the day is a latent variable model. It has a generator again, and you have the data being generated as a function of x, as a function of z, which is, say, z is between this normal 0, 1. This is my x, right? This is often what you end up doing. So, but what happens is, due to the mixing property, mixing in the generator, due to the mixing in the generator, the x's or the z's are not, what do you say? They're not separable. Separable as in, although you selected z to be normal 0, 1, which would be sampled randomly, but G learns non-independent associations between groups of latents and data. So what it does, it could model Z, it could have Z1 and Z2, and use these two jointly to predict one feature, to generate one feature. So this can happen. So this goes and this is lack of interpretability. We are not good at interpreting when you have multiple latents, when you have joint distributions. Lack of interpretability. So when you're not good at interpreting when you have joint distributions, so we always want some form of disentangled representations, and that's all about representation learning. So what we want is, we want some semantic features learned by some categorical latents, say latents C. C could be a group of latents C1, C2, dot, 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 CL, right? And each of this CL could take values in 1, 2, 3, 4 or k classes. Right, so that's fine. So these are just nitty-gritties. You can think of them as latent. So what we want to do at the end of the day is have two things. We have a Z and we have C. Together they form the total latent of late Z info. And we generate data X. Right? This is often what we want to end up doing. Right. So especially what we want from Z is exactly this feature. Where's this? We want C especially to encode for separable semantic features. Features like hair color, skin tone, size of eyes, etc., etc., and which could be we should be able to represent or understand these latents. They'll give you some representations. So if you are doing something in the domain of brains, it could give you each of these latents could have information about different brain regions and so on. And that is very, very helpful in medicine and medical AI. So yeah, so what we want is we want the probability of the latent of C to be again independent. We want the joint distribution of C1, C2 dot dot CL to be the product of I equal to 1 to L. They'll be totally independent. This is all I want to do, right? This is what I want, right? So once I get this, the joint is the product out. And then what can I end up doing is what I have to check now. So this is what we want. Right? And Z, these are uncompressible noise. So which helps you in generation. This will help you in generation. C, on the other hand, will help you control semantics. Right? So one of them could say that a group of these Zs could say that where the image or the type of image I'm trying to generate, C could tell me that now for the same image, please rotate the image. Right? So these type of things which have control over, which is we want to encode it in C. But how will we encode it in C? It is we'll do it in an unsupervised manner. And how will I do it is what I'll show you now. Say my GAN, we just put in Z and C, a naive approach. So I have already drawn this, I'll not draw this. So a naive approach would be to pass both Z and C to the generator. If I pass both Z and C to the generator, and let generator generate an X dash, and then we say real and fake. So what is the problem over here? The generator is not incentivized to keep anything in C. All the information could be in Z itself. That's the idea. So you did not have anything in C, and we could say that, say, what does your generator do? Generator distribution. Generator distribution will learn the probability of X given C and Z. And I can say that the generator can just tell me this is equal to probability of X given Z, completely ignoring categorical semantic information. because there's no way for the model to know what semantic information you want, because the adversarial samples are never coupled with particular features. So if you could do that, then it was okay. That, okay, I have a particular orientation now, and I group all of the orientation in a batch. On the other hand, I have some dark faces on the other batch and so on. So if I could do that, maybe the Cs would learn independent features. But now I'm not doing that. All of them would be mixed. And there's no way for the model to discriminate between what I want as separable semantic information. So if I want to really have semantic information, what we'll have to do is the output, that x tilde of, that is, say, g of x or z comma c, g of z comma c should have information explicitly about c, and we have known how to do that. We can do that by maximizing mutual information. We have learned a lot about mutual information, that mutual information between two random variables x comma y is the entropy of x, how much we know about x, and how much is the knowledge or the uncertainty decreasing when we know y. So it's like how much y gives you information about x. The more it gives you information, more x and y, more entropy would decrease, and more information about x and y would be present in each other, and therefore it would be related to one another. So that's the idea. So we have already shown that this is equal to the joint distribution of x and y log of p of x given y by p of x dx dy. So what I want to do is hence my Info-GAN will have the following objective. The Info-GAN would want to be a generative GAN, and we would always want to maximize the mutual information between the latent codes or the semantics and between the semantics and what else? And the generated data. Right? So now let's see how will we do that. So we know this objective already. This is the GAN objective, l-GAN. And let's see there how we can improve the info or the information GAN objective. So the IG of C and Z comma C, which I'll represent by, say, x tilde, is going to be given by the integral of x tilde comma C. Yes, and probably log of x tilde comma C, or x tilde given C, or I can just write C given x tilde by the probability of C, dc dx x tilde. I have two integrals over x tilde and C. So once I do able to do that, this is the mutual information, and which I can write this as. So again, mutual information. This is a function over the generator. So I'm maximizing the mutual information. Be careful with the signs when you do that. Okay, I'm maximizing the generate, maximizing mutual information. So okay. Okay, so let's do the math. C given x tilde, right? This is x tilde, this is C, log of p of x tilde, C given x tilde, plus, rather minus, p of C, marginalize, this is marginalizing x tilde out, log p of C, I'm just putting the denominator over here, dc dx. This is nothing but equal to the expected value of x tilde from the generator ZC, right? The generator ZC, and you would have the expected value of C dash from, rather let us write this as the expected value of C dash from P of C given X tilde log of P of C given X tilde plus the entropy of C. Right? So as soon as I get that, so the real posterior is not known. Therefore, we can approximate it. We can approximate it using a neural network. Okay, so we can just get a neural network and then just try and approximate it. Okay, so let's just do that. And let's say P of C given X tilde, and we'll approximate it using Q theta of X C given X. So there's a way of doing it. You could divide and multiply by Q C theta and say that, okay, so we can see anytime you do approximate any distribution with a neural network, it's actually taking an upper bound or a lower bound as you do the equations. So this is saying that X tilde given from G, C tilde, C dash from P, we'll say log of C, put a dash over here, C dash given X tilde by Q of C dash given X tilde into Q of C dash given X tilde. And Q, this is a variational distribution or whatever you want to do it as. And as soon as you do this, you will have this term break up into two parts. One is the expected value of X from G, the expected value of C from P, log of P of C dash given X by Q theta plus log of plus the expected value of X tilde given G and expected value of C dash C tilde given P, Q log of Q theta of C dash given X. So this is nothing but the KL divergence, P log P. This P C dash by X log P C dash X Q theta of C dash given X, the integral dx. Okay, so this is nothing but the KL divergence. The expected value of X tilde from generator G of Z and C. And this is the KL divergence between P of C given X tilde and the prediction Q dash of C dash given X tilde or Q theta, whatever C you want to put here, just put a dot. Okay, so plus the expected value of, so I'll just copy the HC terms everywhere, plus HC plus of expected value of. So this is actually not required in from next time. We'll just say we'll approximate it in a neural network. We have done it before as well, but I'm just trying to show that, okay, this is the same idea as doing that, right? Q theta C dash given X plus HC. And this term I can't calculate. This is always greater than 0. So I can say that whatever term I had over here, the mutual information between C, therefore, the mutual information between C and generator of Z comma C is always going to be greater than, because I have to drop this as P is not known. Hence, we will compute it or lower bound it with the expected value of X tilde from G, the expected value of C dash from PC given X tilde. There's a log of Q theta of C dash given X plus HC. So my loss of InfoGAN, okay. Therefore, my loss InfoGAN is equal to minimize over theta, maximize over generator, and Q of expected value of x from Px log of discriminator of x minus expected value of x from Q theta G, and Q theta is different. So this is G log of Z from PZ, C from PC, 1 minus D of G of Z comma C. Okay. Plus log of the expected value of x tilde from G of, again, so this term can be inside this. So we have Z from PZ and so on, Z and C. So this will end up having, is it C dash from log of the expected value of C dash from P of generator of Z comma C log of, it's a tilde everywhere. Q theta of C dash comma x tilde. Okay, so once I do that, I have this two terms. So this is my general GAN. And this term tells that given x tilde or generated data Z comma C, this Q theta is going to predict C dash or C, whatever was the actual C. Let's try to predict that, right? So now, what does it mean if you want to maximize the loss? It means that you're trying to predict whatever C was given in the data. So that is sort of the model already has the information. So the generator must have the information to generate all those images so that the C information is present in the images, right? So the total architecture becomes like this, isn't it? So now the generator, you sample Z from, so the architecture becomes the generator architecture. It's like quite simple. This is my generator architecture. You sample Z from PZ, right? And you sample C from independently from PC1, PC2, PCL. These are could be IID, K category 0, 1, 0, 0, 0, for example, say 10 categories each. You could just give them a one-hot encoding or things like that. And you could say that, okay, my first letter is first encoding is belonging to the kth category, second one belonging to the lth category, and so on. So this is P of C, which is due to independence. You can write it as a product of this. You sample these two, get Z, C, then pass it through this a discriminator T, which predicts, and again, this will also have X, real or fake. But this should be, you should be able to predict the C from this generated data. So this is my Q theta, and this will give me the C, the input C. So what it is actually a classifier guidance. So, okay, this is the classifier guidance that I'm using. So the classifier actually tells you the loss. This is how you convert an idea, mathematical idea, first that I want to improve the mutual information. And then down the stream, you get a loss function. You derive the loss function. First, you have this graphical model. You derive the loss function. And then you implement it using a neural network and show that get the intuition. Final step is the intuition of the neural network. The intuition of the implementation is the predictor of the latents, which is called a classifier, enforces the generator to have information about latents C in X in X tilde. So it's like a classifier guidance, again, like classifier guidance. The classifier guides you so that you could have all this independent axes of C, and then each of the C values could represent a particular feature in the data and so on. So let's take an example and see what the paper shows. So if you could see that the C1 could be one category, right? So it could say here it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 categories. So C1 has this 10 categories. So if the first category is 1, it is going to output a 1. Right? The InfoGAN is saying that this C1 is encoding for the digit type. Similarly, C2 again could have 10 categories. So C2, the latent C2 is telling me how much orientation should I have. Say I could have minus 45 degree to 45 degree orientation in writing a letter. And it is learned. It is the surprising thing is, it is learned end to end in an unsupervised manner. So how do you do this? So what you do is you see the values of C where it maximizes and you put the values. How do you graphically do this? So you select CI and you say, okay, what are the canonical representations? Say all the values for which, say the first latent was 1, right? Okay, the second latent was 1. And then these were all the values. So and you plotted them here. So it's the C2, the first or the second latent. This was C2 and all the images for which the first latent was 1. This is C2, all the latents for which the third latent was 1. This is like 0, 0, 1 and all these. And this is like 0, 0, 0, 0, and this is C2 is like this and so on. So each of these clearly has this information about rotation. And the first one has rotation about information about the digit itself. So this is clearly showing that each has semantic information, which is clearly shown, and the model is able to capture that relevant. And you can use it for medical AI, and the model will do immensely well in understanding what are these features that could help you understanding structures of the brain and so on. Okay. So the other variants or useful variant is called a Bi-GAN. For Bi-GAN and CycleGAN, we'll just do 10 minutes of an understanding of the Bi-GAN and the CycleGAN, and we'll stop. So see, till now, we have learned a mapping from Z to X, right? We have learned a generator map from Z to X, right? So this is my generator. But there is no way, the idea is, the drawback, there is no way for us to know which X's are similar. We know which Z's are similar, but we don't know which X's are similar. So we want an encoding model also. And what does this encoding model do? The encoding model will learn, an encoder will try to convert the X to Z. So what will I do is, say the two cat features, say cat1, cat2 will be together, and dog1 and dog2 will be together. So if I see in the representation space of Z1 and Z2, if I have two latent categories, so they will be sort of represented like this. This is my cats and these are my dogs. Okay. So now what should I do? There's an encoder and there's a generator. So what typically I would want is that the generator, so let us say the generator is G and the encoder is E. So typically I would want that G of Z, right, should be equal to X. Similarly, I would want E of X for the same X to be equal to Z. In other words, I would put this value here. I take encoder on both sides, G of Z, I should get E of X, which is equal to Z. So therefore, I should be able to say that the encoder should be an inverse of the generator. This is what I desire. And I'll just show you the architecture of how you got to do it. So it's like, and similarly, this is way one, and the other processes, I would also weigh like that. I would also want that, say the encoder value of a particular Z or encoder value of a particular X is equal to Z. X tilde is Z tilde. I would want G of Z tilde to be equal to X tilde also. So with this as well, I will see that the encoder or the generator of the encoder, so I'm just putting it here, of X tilde should be equal to X. Both ways it should link to this same equation that I have. Right, both ways. So now how would I do that? I would do that using this following architecture that I have. These architectures, you can see the fair architecture there, but I'll draw the architecture over here. So the architecture is, I have this encoder. You can see the loss later. And this encoder is going to take values of X from Px, the data distribution. And this is going to output me Z, right? Which will be in the PZ distribution. Because you can sort of say this is Z tilde, which will be very similar to the PZ distribution, right? It has to be close. So you could write this as encoded value of X of Px, but this should be approximately equal to Z tilde. We have to enforce that. The other thing that I have here is this generator. And this generator would take values in Z, which is actually in the Z distribution, P of Z, and it would be output me X tilde in the P of G distribution, PG of Z distribution. PG of Z distribution, right? So this is what I wanted to output, and I want this to be very close to the PX distribution. So to make them close to one another, what should I end up doing is I would ideally use the same idea of a discriminator, right? I would use a discriminator, but in this case, I would do a trick. And the trick is as follows. I would pair things up. I would want, what is my desire? My desire is X and Z pairs must be consistent. What do I mean by that? So X could be from PX distribution and Z could be from so there could be multiple E theta of X distribution, right? So Z, where X again is from PX. So this is also actually, this is in the dimension of Z, right? So this we want that this should be actually, in the Z distribution. We want that, right? So similarly, this is way one. We want this tuple that is generator of Z, which should be in the X distribution. So this should be very similar. The generated data should be similar to the real data. Just P theta should be equal to Px and E theta should be equal to Pz and Z distribution. So we will pair things up like this. So we have real values of X. So real values of X, right? And what will I pair this with? Real values of X. And I'll just pair that with the encoded value of so this is a pair of X comma encoded value of X, right? Similarly, I'll pair X tilde this is X tilde or G of Z and Z. So this discriminator will discriminate between pairs of data and latents. Right? This is discriminate between pairs of data and latents. And clearly you can see the fair architecture, and this is clearly this discriminator takes in the value of EX and X and GZ and Z and so on. Right? These two values, this is exactly what I'm trying to do. So this is GZ and Z and this is EX and X. The discriminator predicts between these two. And it can be shown that again at optimality, Jensen-Shannon divergence is 2 log 2 and this is D star is 0.5. And once you have D star equal to 0.5, it can also be shown that G indeed gives me E star. And empirically, so this is already proved. And this, you can look at the paper, but it is very simple because pairwise, this two has to be same and this two have to be same. So therefore, by construction, it should be true. Now we can see that empirically as well. So you can clearly see now, say, so let us take this example that I have over here. This is G of Z. And we'll try to understand what G of Z is. So a G of Z for a particular value of Z is just some generated data. So now I take some input samples. So I took some input samples. And when I took some input samples, I pass it through the encoder to see my claim. So I pass it through the encoder, E theta, and I get EX, E theta of X. And these latents should be in PZ distribution. I pass it through the generator, G theta, and I get G theta of E theta of X, which is again in the PX distribution. And I have shown that this model that I've trained, indeed, so this is indeed equal to X. So these two X, there is consistency between the X. The X showing G equal to E inverse. So you can clearly see for 0, it generates 0, for 1, 1, 2, 2, and so on. So most of these are correct with a few exceptions. I don't find exceptions as well, like one exception here and one exception there, but mostly they're all correct. So this model is able to, by this structure of this discriminator, this encoder and this generator are able to talk amongst one another and generate inverses of each other. Finally, before we end, we'll see cycle-GANs. don't know why do I have so much space, but okay. CycleGANs, what it says that, so say you have a sentence that is written in your English and you want to transform the data into Shakespearean English. This is very similar in cases of images. So for example, if you have a photograph and you want to convert it into a painting, if you have an image of a zebra and you want to convert it into horses, you want to see that how the place looks in summers versus in winters and but do it naturally. So it's actually transforming one variable to the other. This is this idea of change of styles while keeping the idea of change of styles, keeping the semantics similar, is CycleGAN. The idea is instead of sampling noise distribution, why not learn a generator that takes in a value x1 and gives you x2. This is style 1 and this is style 2. So for example, this is a natural image and this is a sketch. Often can be used in domain adaptation, things like that, but that you can study it later. But yeah, this is the idea. So what I want is, say I have two distribution P of X and P of Y. I want a generator that will convert Px to Py, say generator X to Y. I want another generator which will convert Y to X, right? These are the type of things I want, and hence it's called a CycleGAN, right? So there will also be a discriminator, say a discriminator dy and a discriminator dx predict or categorize Py and G of X to Y Px. So it will try to differentiate between the P of Y and the transform distribution of X to Y. Similarly, Px will try to categorize between Py or Px and the generator of Y to X Py. Right, so this is the idea. So this is exactly what I've drawn: the generator for discriminator, generator for the generator for the generator for the discriminator, and the generator for the, what am I saying, discriminator for X and discriminator for Y, and the generators Y and X. Right, the CycleGAN therefore would have two GANs. One GAN objective that would take in values from X distribution. So here you would have Y. So GAN 1, Y from P of Y, X from P of X, and you would use the generator X to Y and you would pass X. And a discriminator would predict between these two. For this GAN, I would have X sampled from Px, Y sampled from Py, and G of Y to X Py. And you will try to discriminate between these two. So you can clearly see I will have these two objectives which I've written. I'm not going to write the entire GAN objective again. You can just implement it directly. For X to Y, right? I'm going to have the discriminator for Y. And you can clearly see I'm using the discriminator for Y, and the discriminator for Y is going to discriminate between actual Y and transformed version of Y. Transformed version of Y from X. Similarly, the X to Y I will have a discriminator dx, which will discriminate between actual x and transformed versions of x from y. Okay, so you can see the discriminator y exists, and there's this generator x, gx, this is gy, which takes in value from y and gives x. This takes in value from x and gives y. Okay, so now I have these two GANs, but the problem is I can have loss as loss g1 plus loss g2, or gxy and gyx, but no one is enforcing reconstruction. That is consistency. So what do I mean by consistency here? The consistency means that the g of x, so g of x should be the inverse of g of y. So this is a way to make the GANs talk. Make the GANs talk, right? You can make the GANs talk in this way. And how do you make the GANs talk? So you are saying that for an input image x, if you transform it to y and retransform to x, there should be minimal loss. This is the idea. So therefore, so g of x of y of x should be approximately equal to x, right? So therefore, we will introduce two losses, which will say that gx of gy of x minus x as the loss where x is sampled from px. And the other loss would be gx of y gy should be equal to y, the expected value of y from py, gy of gx of y minus y, right? And these two are called the consistency loss, and that's what I've written over here. Okay, so that gx is equal to gy inverse, and GANs can talk. So with that, we have come to end of various different type of classical GANs, including InfoGAN, CycleGAN, Bi-GANs, f-GANs, JS-GANs, and normal GANs, DC GANs, and so on. The next class will be ending GANs with Wasserstein GANs, which is a completely different measuring technique. And we'll also see the implementation of GANs, and we'll try to enter autoregressive models. If you have any question, please feel free to put them in the channel, and I'll answer them. And we'll answer them probably in the doubt clearing sessions, and we'll take them one at a time. So yeah, in the next class we'll be seeing the implementation of GAN. I'll upload the code and the results as well. So with that, I'll stop recording and see you in the next class.